Hi students, in this video we're going to go over section 4.9 additional set definitions. So our goal for this video is to discuss additional definitions involving sets. First definition is disjoint. We've actually seen this one before, so we're going to revisit it. Set A and set B are called disjoint if and only if they have no elements in common. So symbolically, this is how we will write it. A intersection B is the empty set. Example 1. Determine where the following pairs of sets are disjoint. So for part A, we've got set A is 1, 2, 4, 11, and set B includes elements 1, 3, 5, 7, 9. It looks like these are odd integers, so you can assume that the next element after 9 is 11, and so they do have something in common. So their intersection, A intersection B, is equal to the set containing the element 11, which is not your empty set. Since that's the case, these are not disjoint. Sets A and B are not disjoint. There is some overlap there. Now let's look at part B. Set C contains the elements 2 and 4, whereas D contains the set containing the elements 6, 8, 10, and 12. They have nothing in common. So here the intersection between C and D is the empty set, which you can write either this way or this way. And since that intersection is empty, then C and D are disjoint. Mutually disjoint. So sets A sub 1, A sub 2, A sub 3, and so on are mutually disjoint if and only if no two sets A sub I and A sub k with distinct subscripts have any elements in common. Basically, it means if we have a bunch of these sets, if you take any two of them and they're disjoint, then all of these are mutually disjoint. So symbolically, I have it written down here. If you take any set A sub I and A sub k, where I and k are different subscripts, and you do the intersection, if you get the empty set, then they're all mutually disjoint. Also, this is called pairwise disjoint or non-overlapping. Those are some other ways this might be described. So, for example, 2, if A sub 1 is the set containing elements 1 and 2, and A sub 2 is the set containing the elements 3, 8, and 10, and A sub 3 is the set containing the elements 4, 5, 6, and 7, are these sets, are A sub 1, A sub 2, and A sub 3 mutually disjoint? So when we take any two of them and they're disjoint, then these are going to be mutually disjoint. So you have to be able to take any two. So I can do A sub 1, A sub 2. I could do A sub 1 and A sub 3. And I can also take A sub 2 and A sub 3. So that's how I'll pair them up. So this is all the different ways you can take two of the three sets. And then if you do the intersection between those, these all have to be the empty set for them to be mutually disjoint. So if we're doing the first one, A sub 1 intersection A sub 2, do these have anything in common? No. So their intersection is going to be the empty set. If you take A sub 1 and A sub 3, does the intersection contain anything? No, that's empty. And then if you take the last two, A sub 2 and A sub 3, do they have anything in common? No, so their intersection is the empty set. So since when you take any two of them, the intersection is the empty set, then these are all mutually disjoint. So A sub 1, A sub 2, and A sub 3 are mutually disjoint. So they're all non-overlapping. So if you did a Venn diagram, so we can visualize this, and you have like this universal set. If you have A sub 1, A sub 2, and A sub 3, they're all disjoint, no overlapping. So that's why sometimes this is referred to, instead of mutually disjoint, it'll be referred to as non-overlapping sets. Definition for partition. So a finite or infinite collection of non-empty sets, A sub 1, A sub 2, A sub 3, and so on, is called a partition of set A if and only if these two conditions are met. A is the union of all the A sub i's, so the union of all these sets here. So in other words, A sub 1 union, A sub 2 union, A sub 3 union, and so on is equal to just set A. And 2, the second condition is that the sets A sub 1, A sub 2, A sub 3 are mutually disjoint, which we just went over. Example 3, we're going to let A be the set contain the integers 1 through 8 inclusively. Determine which, if any, of the following are partitions of A, and if not, then why. We'll do a little explanation. So let's look at part A first. I'll take that down here. So we have a set containing 1 and 2. That can be A sub 1. Then we have a set containing 4 and 6. That can be A sub 2. Then we have a set containing just the element 5. That can be A sub 3. And a set containing the elements 8 and 7, which can be A sub 4. So the first condition is if you take the union of all of these, A sub 1, union A sub 2, union A sub 3, union A sub 4, does that equal set A, this set here? And would it? We would not get A. This is not equal to set A. And this is because none of these here contain the element 3. The element 3 is missing. So this is not a partition. So we're going to say no, not a partition of A. And our first condition is not met. No set contains, I'll put no set contains element 3. Therefore, first condition not met or not satisfied. Now let's try part B. So for B, we have 1, 2, and 5. That can be A sub 1. Then we have 4 and 6. That can be A sub 2. And then we have 3, 7, and 8. So we have to check, that will be A sub 3. So we have to check those two conditions, make sure those two conditions are met or satisfied. So the first condition, if you do A sub 1, union A sub 2, union A sub 3, do you get set A? And in this case, yes. You would have 1, 2, 3, 4, 5, 6, 7, and 8. They're all in there. So that first condition is met. Is the second condition met? So I'll put a little 1 here. The second condition is that A1, A2, and A3 are mutually disjoint, which they are. If you take any two of these, you're not gonna find any that overlap. Their intersections for any two of these are always the empty set. So I'm just gonna say A1, A2, and A3 are mutually disjoint. So this is a partition of set A. All right, last one like this, part C. So we have 4 and 7. That can be set A sub 1. Then we have 1, 3, and 6 together. That's A sub 2. And then we have 2, 3, 5, and 8. That can be your A sub 3. All right, is this a partition of set A? If you do the union, you do have 1, 2, 3, 4, 5, 6, 7, and 8. The union of these three sets would, yes, give you set A. So that first condition is met. But what about that second condition? Are these all mutually disjoint? And they're not. So two sets, specifically A2 and A3, contain the element 3, right? So A sub 1 intersection, A sub 2 intersection A sub 3 equals the set containing the element 3. It's not the empty set. So these are not mutually disjoint, so it can't be a partition. So I'll put not mutually disjoint. And we'll say not a partition of set A. Definition for power sets. So given a set A, the power set of A, just symbolized like this, is the set of all subsets of A. And previously we did go over finding subsets of a given set, so we're just kind of expanding on that. So for example, 4, we're going to let A be the set containing 1 and 2. B is going to be the set containing the elements 2, 4, and 6. And we're going to find the following. So for part A, we want to find the power set of A. So it's going to be the set of all subsets. And as a reminder, if I'm trying to figure out, well, how many subsets would I have if I have just 2 elements? It would be the number 2 squared, which is going to be 4. You're going to have 4 subsets. This was covered in a previous section. So we'll have a set containing just 1, element 1. We'll have a set containing 2. We'll have a set containing 1 and 2. And then let's not forget the empty set. What about part B? The power set of the intersection between A and B. So this would be, what's the intersection? That would be just containing the number 2, right? That's just a set containing the number 2. So we have 2 to the first. Remember, the exponent here is the number of members in your, or elements in your set. So we're only going to have 2 sets in this power series. We're going to have the set itself, which is 2, and then the empty set. And then part C, what's the power series of the power series of the empty set? All right, so this is going to be equal to, we're going to work our way from the inside out. So I'm going to do this part first. What's the power series of the empty set? Well, it would just be the subsets, the set of subsets of the empty set. So it's the set containing the subsets of the empty set. Well, the subsets of the empty set is just the empty set. And if this notation is a little confusing, right, you could just, these innermost brackets represent an empty set, so just maybe draw the symbol for the empty set. That might be easier. And then you still have to do the outside, the power of that, the power set of that set. So up here, well, I'll do it both ways, but up here, you're looking at finding all of the subsets of a set containing the empty set. So this would include the empty set and this set containing the empty set. And you can see there's so many braces, so this would get a little confusing. So down here, it might be easier to use that symbol for the empty set. So it would be the empty set, and then the set containing the empty set. One-to-one correspondence. So 2 sets that have the same cardinality, the same number of elements in them, can be placed into one-to-one correspondence. Set A and set B can be placed in one-to-one correspondence if every element of set A can be matched with exactly one element of set B, and every element of set B can be matched with exactly one element of set A. Example 5, determine where the following pairs of sets can be placed in one-to-one correspondence. So for part A, set A is the set containing all elements X such that X is a US state, and set B is the set containing all elements X such that X is a US capital. So we know that the cardinal number for set A is 50, 50 states, and B is the cardinal number for set B, the US capitals, also 50. So their cardinality is the same. So A and B can be placed in one-to-one correspondence. Part B. C is the set containing the elements X, Y, and Z, and D is the set containing the elements A, B, C, and D. So the cardinal number of C is 3, and the cardinal number for set D is 4. So as soon as their cardinality is not the same, these are not equal, then they cannot be placed into one-to-one correspondence. So we'll say C and D cannot be placed in one-to-one correspondence. Definition for infinite sets. So earlier in this chapter, we talked about finite set, and at that time, I think I just mentioned that infinite set would be a set that's not finite. So this is a better definition. An infinite set is a set that can be placed in one-to-one correspondence with a proper subset of itself. So example 6, show that the following set of natural numbers, right, this is your set of natural numbers here, is an infinite set. N here just represents some integer, like an element later on that's not listed. So we are going to take that set of natural numbers and we are going to find a proper subset. I'm going to write proper subset. So a set that's not equal to the set of natural numbers. So I'm going to remove the 1, and that's how I'm going to get my proper subset. So I'm just going to have 2, 3, 4, 5, dot, dot, dot. This would be n plus 1, and so on. Doing n plus 1 here, right? This should make sense, right? If this is a 1, this is 2. This is 2, this is 3. So if this is n, this is going to be n plus 1 more than it. And then I'm just going to draw arrows to show the one-to-one correspondence. So I'm matching up the element 1 in the set of natural numbers with the element 2 in the proper subset. 2 is going to get matched with 3, 3 was 4, 4 was 5, n was n plus 1, and so on. You can continue in this manner infinitely. So a one-to-one correspondence exists between the set of natural numbers between n and a proper subset so the set of natural numbers is infinite. All right, that's it for this section. Try out the homework, and I'll see you in the next one.